Imagine a fuel that produces no smoke, no carbon, and no pollution, only water. This fuel contains 3 times more energy than gasoline. It sounds almost too good to be true, right? But this fuel already exists. It's hydrogen. And if we could use it effectively, hydrogen could help us move towards a future aligned with some of the most urgent goals. The United Nations Sustainable Development Goals, particularly number 7, 9, and 13, which are affordable and clean energy, resilient industry and infrastructure, and meaningful climate action. Yet, despite all this promise, hydrogen still seems irrelevant on our everyday lives. I'm Gabriela Kuswadi, a chemical engineering student from Universitas Pertamina, and I want to share one idea that could help bring hydrogen closer to reality. In fuel cell electric vehicles, hydrogen reacts with oxygen to generate electricity, and only producing water as its byproduct. No carbon emissions, no exhaust fumes. So, if hydrogen is so powerful and so clean, why don't we see hydrogen cars everywhere? The problem isn't the fuel itself, but it's also on how we store and deliver it. Hydrogen is an extremely small and light molecule. To store enough of it inside of a vehicle, we usually compress it to very high pressures. This means thick tanks, expensive materials, and complex safety systems. Over time, hydrogen can also even weaken metals, a phenomenon known as hydrogen embrittlement. On top of that, we will need to build thousands of refueling stations to accommodate FCEVs across roads and highways. All this makes hydrogen seem unsafe and difficult to scale. But what if we store hydrogen in a smarter way? What if we store hydrogen inside porous materials? Materials that have tiny microscopic tunnels that can absorb hydrogen much like how sponges hold water. One promising example of these porous materials is metal organic frameworks or MOFs. MOFs are remarkable because they contain an enormous number of tiny tunable pores. In fact, a small amount of MOF can have an internal surface area larger than a football field. This vast surface area is what allows hydrogen to be physically absorbed onto its surface. ZIF-8 is an example of a MOF material that is chemically stable, is relatively easy to synthesize, and has been shown to meet the US Department of Energy targets for material-based storage. By filling tanks with ZIF-8, hydrogen can be safely stored inside these tiny pores and be released when the fuel cell needs it. However, improving material storage alone is not enough. We also need to think how hydrogen reaches these vehicles. This is where the concept of hydrogen tank swapping stations comes in. You may be familiar with battery swapping in electric vehicles. Now imagine applying the same concept but for hydrogen. Instead of waiting for a car to refuel, hydrogen tanks could be simply swapped and drivers could continue their journey almost immediately. By combining MOF-based storage and tank swapping stations, we create a solution that is safer, faster, and potentially more affordable. This innovation is not just about discovering a new material, but reimagining an entire system of how hydrogen is stored, delivered, and distributed in many places. And by doing so, we create a transportation system that supports affordable and clean energy, stronger infrastructure, and meaningful climate action. Because remember that fuel we imagined in the beginning? A fuel that could be one of our best chances for a carbon free transportation. Sometimes the real challenge is not only about discovering something new, but by designing a system that allows us to use what we already have. And perhaps hydrogen will no longer be a fuel of the future, but a fuel that moves us forward. Thank you.